In terms of, just to have an idea, that in terms of weight, also internal combustion engine is about 100 to 250 kilograms, whereas an electric motor would be just 75. And then the pollution level would be much lower. So silicon carbide, a lot is being driven by the electric vehicles. And this will continue, as we know. Then gallium nitride, we already heard, but I will just put the numbers. I think some numbers were already indicated by the professor. If we see on one section, which is the RF section, and we have defense and telecom infrastructure, quite a lot user of that, is about in the range of 700 million to 1 billion. It will grow 2.5 times in next 5 years. So would be reaching about $2.5 billion if we look at the RF side of gallium nitride. On the power side, where the consumer is a big, like fast chargers, for example, which was already indicated, and this is at the moment is about 100 million, but this is also going to become about $1 billion as we will reach for next 5 years. So if we are putting everything together, there are two elements here. One is that we absolutely need this technology, because otherwise the more and more power we are going to consume, if we do not gain in the efficiency of that, it would be pretty bad for our planet. And great news is that this is available today. And we should utilize it more and more. And the business case is very clear. So in that context, I would like that we open our panel and going from one side, even starting from the research, materials, way to the applications and all the challenges there. So once again, very pleased to have this very diverse panel in front of us. So maybe I start with Seema, from you, to begin with on the right side from SSPL.
So thank you, Vivek. It was great listening to Professor Umesh Mishra just now, because it felt so much, I felt so much at home with compound semiconductors. We've been listening to silicon industry and how it is growing over the years and how complicated, almost equivalent of about 120 stories of a building. I would say that SSPL, Solid State Physics Laboratory, it was born out of a remarkable vision about 60 years back to build up semiconductor capability and a knowledge base in the country. And what we feel is that long back, somewhere in 70s, we thought that silicon is already a mature technology, and so it is the compound semiconductors that we should move forward with. And as we went on, about, after developing a few circuits, devices for RF applications in gallium arsenide, what we felt was that unless you have a foundry, a fab, where you can take your technology, you can actually not have your technology can actually just die down. You built it, but where do you take it? We did not have anything like that in India. And so about 30 years back, I think around 95, we went ahead to develop GAETEC. And GAETEC has been delivering gallium arsenide MMICs for defense and space applications. So once the technology we could see in production, we went on to gallium nitride and silicon carbide. And out of experience, I would say that since our mentors always thought that if you're developing a technology, it is very, very important to develop the material as well. So right from ingots to epitaxy to device design and device fabrication, and then going on to measurement, and then say the process design kit based on the GAETEC Foundry. We've seen it with gallium arsenide, and we are doing the same with GaN now. But what is very important is that silicon is really very, very mature and very, very complicated. Whereas compound semiconductors, because as you would have heard Dr. Umesh Mishra mention, it is just by changing the growth of the material, you can actually, without going down to, even if you go up to about 250 nanometer, you can reach frequencies in the KU band, and you can deliver such high powers with such high efficiencies. So the promise is very high. And what we have is that in the power sector, again, silicon carbide, gallium nitride is holding a major promise. Also, people have started working in the digital arena, seeing how gallium nitride can be utilized there. We also have lighting, of course, is something where gallium nitride all started. So there is a very, very vast area. Now quantum is coming up. Gallium nitride is showing promises to be utilized even in the quantum technologies. What I feel is that, yes, this area definitely needs thrust. And if we have a foundry, a fab in compound semiconductor, the positives are that most of the universities, the IITs, the IIC are working in this area. So we have a very good human resource available with this kind of expertise that we can leverage. And the challenges are that the infrastructure that is needed for this, we have limited expertise within India. Of course, I heard Mr. Dalal saying that his father was involved in the building up of many clean rooms within India. But I would feel that there is a limited expertise to give that kind of infrastructure or the facility that is required for a fab, may it be silicon or may it be compound semiconductor. For compound semiconductor, I would say that yes, we may not require to be dependent totally on foreign, import of technology. Silicon, there is absolutely no other option. You have to get it from outside. But once we have the fab, how do we maintain it? Because if we want to get maximum out of minimum effort from the workforce, it is very important that all your equipment and your facility is continuously running. And therefore, we need experts in this area as well. Then the semiconductor equipment, we are totally dependent on foreign resources. There, the export licenses, the numerous delivery period extensions, and sometimes the after-sales support all become challenge. And therefore, it is very, very important that we have some policy decisions where either we go ahead with very long warranty periods or we have the OEMs establish their spare part service centers here in India. I would just say that this is the time that requires a lot of planning. And I also hear that this is maybe the third of the efforts, which is really wonderful coming here. It is so overwhelming to see the numbers that are involved in the semiconductor industry within India. But this is the time to actually plan and see what were the reasons, what were the causes that the first two attempts or maybe a first few attempts did not actually have, let India have a fab. And we must have one here now. So it is learning from that. And whatever way we can make the establishment of this technology easy for the people who are bringing it here, it is very, very important. We have to depend on very intelligent collaborations, which is a must for bringing any fab to India, and also a major support in terms of equipment, in terms of chemicals, gases. I think that since yesterday that has been discussed. And there I would say that because there is limited demand that exists within the country, we do not actually have people who are working in this area, but once we have a good semiconductor setup within the country, there is no dearth of expertise even in this area. So with that, I would just say that we go ahead with Vivek.
Thank you very much, Seema. And I think that being there and really doing the kind of technology development and some of the challenges you highlighted, are quite important, particularly if we would like to really develop it in a stronger way. So let's now move towards the left side of mine, where we have Anant and the GAETEC model, as Seema was already mentioned. And would be really nice to hear from him the challenges, and particularly on the overall ecosystem. How do you see in India, how is playing it out?
Yeah. Good afternoon. First of all, I think the government has taken a very necessary step in establishing the foundry system in India, fabs in India, and I think Mehta is doing a great job trying to bring together the stakeholders here in today's meeting, as well as in the previous as many meetings that we have had with Mehta. So all the best to all of us. We will be able to do a great job to our nation. Now coming to the compound semiconductor, the way forward is the theme of today's panel discussion. And compound semiconductor actually is like in silicon, there are technology nodes. In compound semiconductor, besides the same technology nodes in terms of minimum feature size, there is a material node also. Like in compound semiconductor, there is indium phosphide based devices and MMICs. There are gallium arsenide based devices and MMICs. There is gallium nitride based MMICs. And also to a great extent now silicon germanium BiCMOS is also entering the field for certain front end radar applications, seeker applications. So I think the totally different paradigm compared to a silicon fab. This is more of a strategic and necessity for any country to have its own basic minimum requirement in this area. Like other than the defense applications in radars or electronic warfare, there are a lot of commercial applications. A lot were highlighted by Professor Mishra, who the team is already a leading team for gallium nitride and silicon carbide activity. Then there is a power conversion, which we have been talking about, the minimizing the losses using gallium nitride based power switches technology. Then we are also entering into a paradigm of terahertz technology, where compound semiconductor will play a very big role, and subsequently the quantum computing that we are entering, and in the world over is a huge amount of work being done in quantum computing, and the low temperature operations of these devices, cryo applications of these devices. So a lot of things are required to be done to be in tune with the time that world is progressing, and there are certain things which India needs to take at this time. We may require more than 2 or 3 additional kind of a compound semiconductor fabs which may focus on various aspects. Particularly the strategic aspect has to be kept separate, because these are the devices and MMICs which are not supplied to the country, any country. It is a IP of that particular country who will not share that easily with any other, unless we have a government to government understanding. So that is one aspect that we should focus on, that wherever there is a need and we don't have a way out, there should be a government to government understanding. And we also need to focus on all this compound semiconductor and start beginning to build certain fabs which are catering to different applications. A lot of manpower and institutes are working in this area, including IITs, regional engineering colleges, and IISc, for example, is taking a very big lead with the GEC approach. So I think people are there and we need to work together to come at a good solution for our country. And the biggest challenge to establish country is the supply material, which has been discussed n number of times since yesterday. For compound semiconductor, even the wafers or the substrate material is also a big challenge, besides having challenges in terms of photochemicals or other high priority material used for electronic fabrication. So we also need to have a foundry which can cater to this substrate material. Though we have some indigenous effort in development, but to start with, we need to have a head start. We should have a proper substrate like silicon carbide or gallium arsenide or indium phosphide type of a substrate manufacturer. The technology know-how about the growth, etc., is always available in India because many groups are working in this area. And coming to the chemicals part, I think since yesterday we have been discussing it, and India is a very big chemical industrial base. If you go to the western part of India, the GIDC we call, and maybe we are one of the biggest manufacturer of IPA, which is one of the big chemical, large volume chemical required for semiconductor industry. So it's only a matter of time that we can promote them to purify their material for electronics, their 6.9 or 7.9 grade purification. So I think was talking to some, yesterday to Mehta team, then they said, yes, they are also including this subsidiaries also under this same platform, and they will be given some PLI kind of incentive also. So that's a good initiative, and I think compound semiconductor fab is absolutely necessary for our strategic applications. And long time when DRDO set up this foundry with the technology that we have developed at SSPL, and we brought that technology to production level. Now it's used for space applications also. And I think we have a very good collaboration and support from ISRO in building this fab and using this fab to best benefit of the country. We need much more number of fabs in this field, I think, and this scheme should bring more fabs to India. Thank you.
Thank you, Anant. So I think very clearly emphasis is definitively as a country we need it. The world needs it more and more, as highlighted already. But also there are challenges, and this support from government is indeed very much desirable and applauded. But then the supply chain and ensuring that all across, because it was amply mentioned before that at the end we are quite an integrated ecosystem, just not isolated. So we need to focus on that so that everything can flow. So this is what we heard from both colleagues working here in India, from Seema and Anant. Let's now go over and go to Harshad from Silicon Power to share his experience. He has a very good experience in India, but also now operating from States. So let's hear from him what are the different challenges and opportunities he sees. Over to you, Harshad.
Thank you very much. I appreciate the opportunity to talk about and be part of this esteemed group. I talked to our new Secretary of Electronics about for an hour on a Zoom call, and something that he said was music to my ears. And he said, power electronics is the lowest hanging fruit for India, not only for silicon carbide, gallium nitride, but also for silicon. And this is what we have been doing. So I know a lot of people don't know, and I understand that, but that is why I'm trying to make sure that we know. In Baroda, we have been fabricating silicon power silicon thyristors, diode, and so forth since 1998. And we not only supply to Indian industry, Indian railways, Indian process industries, we also supply to US military. And now we are going forward in terms of trying to learn and leverage the experiences and the lessons that we learn from silicon on the application side, because of the fact that if you look at the customer base, at least in power, you're going to have same customer base in terms of industrial customers who are using silicon as well as silicon carbide or gallium nitride at some point. And to be very honest, I think I'm very pragmatic, because sometimes customers are looking for cost-benefit trade-off. And very likely, they may go with a hybrid module first, with a silicon carbide diode and a silicon thyristor, because of the fact that silicon carbide diode provides 95% of the benefit of all silicon carbide module at only about 20% premium in price. So when you look at the cost benefit, sometimes you can't ignore the lessons we learn and the silicon expertise can help us, how we can commercialize silicon carbide as well as gallium nitride. At Ratan Shah, which is my company in Baroda, we already have installed a silicon carbide epi reactor, and it should be able to produce silicon carbide epi layers for not only for India, but also for global industries. And that would start sometime in July of this year. So we have a three-phase plan. Phase one is a silicon carbide epi. Phase two is silicon carbide fab. And phase three is silicon carbide packaging. Because as Professor Mishra said, thermal management is very, very important as well. And silicon power has for years, we have a very substantial intellectual property in terms of how to take advantage of high temperature, lowest inductance on the power device packaging. And so we are moving forward in phase one. We already have started phase three effort. And I have a fab in US, which I purchased from Microchip, that does silicon carbide fabrication. So that's the plan in the beginning, near term. And then as we move forward, we would have the silicon carbide fab as well in Baroda. And that's the plan. Ratan Shah also has applied and preparing a proposal for gallium nitride, specifically for power applications and so forth. I totally agree in terms of energy efficiency. I totally agree in terms of having a fab in India so that the talent coming out of our institutes can be fully utilized. Our very first technical person on the EPI was from TIFR PhD, and he had an issue. He said, where do I go? He didn't want to go to Singapore or outside India. And he found a place to come to Baroda and work for us. So we are doing everything we can as a small company. Ratan Shah has been in the business in power semiconductor since 1969. It's been a public company since 1984. He's been an IR licensee from 1984. And then when I purchased Silicon Power from General Electric, I also transferred high power silicon thyristor technology to Ratan Shah as well. So I think we are trying to, my motto is commercialization. My passion is commercialization. And I believe in manufacturable, usable, sellable technology. And a second thing I have, which is not very smart business thing to do, but I also believe in why not. So in 2000, when there were no fabs in India, we transferred GE Silicon Fab, lock, stock, and barrel. It took us a year, but we are successful, and we plan to do same thing for silicon carbide as well as gallium nitride. Thank you very much. Appreciate it. At any question, I would take it anytime.
Thank you so much, Harshad. So we can clearly notice that the deep experience you have, and now as the time is becoming even more ripe for the acceleration of this would be definitively very handy for also our other colleagues who are in this venture. So thank you, Harshad, and then we will return back to you in case of questions. Now let's go to the other side, that when we need to develop a new technology, how challenging it could be. Professor Mishra actually indicated that, but it is my pleasure to invite Primit, again from States, to be able to share with us the experience of Transphorm. Primit, for you.
Thank you, Vivek, and pleasure to be here talking about how do you realize value with new technology, and in this particular case, gallium nitride, which is the highest efficiency semiconductor for power conversion. So first of all, as many of you are aware, semiconductor development is a marathon, not a sprint. What are some of the requirements? Vivek and Seema and talked about it. Anant, human capital, financial capital, intellectual property, infrastructure, and infrastructure for semiconductor. Ecosystem, not just a semiconductor, but from chemicals to the semiconductor, to the user, to the application. Markets, and then policies. So I color-coded this stoplight chart, red, yellow, and green. Red means not quite present in India, and green, it is available, and yellow is improving, right? So human capital for semiconductors human capital is plenty, extremely well good in India, but not so much for semiconductor if you look at it from an overall perspective. Similarly, infrastructure and policies. What is entailed in a new semiconductor like gallium nitride, right? And it is a minimum 10 plus year cycle to get there. First of all, device development and operation validation, followed by manufacturability, realization, and product qualification. That's just kind of the beginning. You do all of that. Then reliability methodology and lifetime establishment, application development and marketing, QA, quality assurance for very low defect density. Power is a very unforgiving market, and PPM level failure rate. We have a Transphorm less than 0.2 fit rate, failure in time per billion hours of operation, with more than 40 billion of hours of operation with our customer system in the field, which leads to happy customers, is a sign of good technology. Field failure, very low field failure rates from mass production ramps. And at the end of the day, satisfying multiple growing markets with performance and cost benefits. And on the right side is shown some extremely large markets for power semiconductors, in which gallium nitride is not only inserted now, but rapidly growing. Smartphones and computers, 5G. 5G for RF, Umesh talked about it very nicely. Electrification, electric vehicles, four-wheelers, two-wheelers, three-wheelers. This is a huge opportunity. And we have a chance to creating business and societal value through technology. And how do you do that? How do you maximize learnings? And especially in a country like India, where this is kind of starting, not so much from scratch, as Harshad said, but in the case of a new technology like gallium nitride, kind of from scratch. Maximize learning, not by starting at the beginning, start at the finish line. And what do I mean by that? What is a typical manufacturing flow? You have the core, very fundamental, this is critical, epi wafer technology and manufacturing, wafer fab, device design, wafer fabrication, OSAT, assembly and test, packaging, design and EMS, application design, EMS, and then system insertion. To do that, if you start from here, it will be a very long time. So start backwards. How do you maximize success? Start with what is existing. Use gallium nitride-based power supplies, converters, inverters for products and systems. Build user confidence today. Then what do you do after that? Establish design centers, or in parallel with that, for application system development with existing state-of-the-art gallium nitride power devices. So grow the market, cater to domestic needs. Then develop OSAT, assembly and test, with known good gallium nitride wafers, with something that works. Ensure packaging success. That takes 1 to 3 years, perhaps. Then come to the complex part, which is establishing wafer fab manufacturing. And not necessarily everything has to be in serial, but this is kind of the flow to maximize success at every step. Establish wafer fab manufacturing, including the associated infrastructure, with proven started epi materials. And then complete the supply chain with epi wafer fab and manufacturing. Right, this way, what you will do is ensure success at every step by using established learning and established successes. And what is the goal at the end of the day? Vivek talked about efficiency. It's exactly similar what I show here. 150 terawatt hours, which is enough for all rural households, can be saved just by using gallium nitride widespread in power electronic applications by 2030. So this is efficiency across the spectrum to create a very lasting impact. And what we are doing at Transphorm and many other companies in gallium nitride, where we are leading the way, is having products, having gallium nitride in power conversion across the spectrum of the power range, from very fast adapters and chargers ramping in the market already today, sub 100 watts for your phones, tablets, iPods, etc., motion control, industrial power, gaming power, two-wheelers, three-wheelers, as you go to the higher power range, data center and communication, the backbone of computing, electric vehicles, renewable energy, UPS, and for the EVs at the end of the day, onboard chargers, converters, and the powertrain inverter. Gallium nitride is a fascinating material. Power electronics is a very large growth market, and not only creating technology, creating business, but creating a long-lasting environmental and societal impact. Thank you, and be happy to take any questions at the end.
Thank you. Thank you, Primit. And once again, I think that the business case is very clear. And also one important aspect is that the ecosystem is important. It's not only a matter of fab, but then we need also rich ecosystem around it. Now let's move to Amitava from Tagore Technologies and hear from him that his experience, particularly from the demand side, because we do have supply side where we have material R&D, development of new technology and fab, but what about the demand side, particularly in India? Amitav, up to you.
Yeah, can you hear me?
Yes, very well. Please go ahead.
Oh, okay. Okay. So basically, I want to focus on the demand side. And in fact, as an example, we'll start with Tagore Technology. So basically, what we did about 4 years ago, we created a team in Kolkata and we started developing GaN IC. And essentially in 4 years, the team started from the defining the IC, they designed it, we sent the design to Taiwan, of course, because we don't have a fab in India, and we got it assembled, and the parts came back to Kolkata. And then it got tested, characterized, and we did the reliability evaluation. And the whole thing actually is done right here in India, in Kolkata. And then we developed the application, and now we are shipping in very large volumes to China. So not importing, actually exporting to China. So this example actually says that we can do compound semiconductor development right here in Kolkata, in Bangalore, in Hyderabad. And essentially what we need now is wafers. So basically, I think this whole proposal from government is exactly very well timed. So essentially from the demand side, companies like Tagore and other companies will come. And I think there is a real demand. And we ourselves can easily, let's say if it takes 2 years to create a GaN fab, we can take several thousand wafers in 2 years and provide the demand. So basically my point is that the GaN fab, if we can make that fab, because we are fabless, so we don't go into the process and how to make it, but assuming that we have that expertise, there will be sufficient demand for wafers. And I think companies like Tagore and other companies coming through DLI schemes will be able to provide the demand pool. Now, I also want to touch on a few other related topics. So for example, once you have this fab and you make the ICs, where do you sell? Of course, we can follow the same thing right now, selling to China and other countries. But for that, we need competitive pricing. So I think we need some sort of incentive from government on wafer pricing, because the input material cost, chemicals and other things will make the wafer cost in India slightly higher. So that needs to be kind of compensated. So that's one aspect. But besides selling GaN ICs globally, I think another big opportunity in front of us is how do we develop a local demand within India? How do we develop demand in India? And basically the EV space and solar space, there's really great opportunity in compound semiconductor. Why? Because the systems are complex, but not as complex as developing mobile phones, right? So a small, good team can develop systems and indigenize the product. But the biggest threat actually is the low-cost import. So nobody wants to develop their own system because they can import a complete knockdown kit easily. And what I found by talking to various people in India is that the quality of these cheap imports are not always good. In fact, the reliability is a big issue. So one proposal I have is that if we can have some more regulatory, like quality regulation and some sort of, and the customers, they demand good quality, then I think we should be able to fight the cheap imports and develop an indigenous ecosystem for consuming the IC. So we can sell globally, or better even if we use the EV and solar space to develop indigenous solution. And we have to make sure that we weed out the cheap imports through some quality metrics. And the third item that I want to highlight is there is this big EMS, electronic manufacturing opportunity in India, right? And if we can define some schemes where they will be incentivized to use ICs which are fabbed in India, that will also give a good avenue for consuming the IC. So in summary, how do we create a demand pool of ICs made in India? So one is we sell globally. Two, we try to develop indigenous solutions and making sure that the cheap imports are weeded out through quality requirements. And number three, try to insert the ICs which are made in India in the EMS system through some sort of incentive scheme. So that's roughly what my thinking is, the way forward to create a demand pool to support a fab, because fab has to be full, otherwise the cost will not be favorable. And I think companies like Tagore and similar companies will come up with the DLI scheme, should be able to support the fabs. Thank you.
Thank you, Amitava. I think once again we have a very clear emphasis that we need the ecosystem, not just parts of it. And here Amitava brought one important aspect, because many times when we look at the demand, we see the demand as consumed by the consumers. But for the industry in semiconductors, there have to be system designers and system manufacturers in between to bring the real demand over there. So thank you. I think Amitava, then later on we'll get back once we are through our panel. So now let me move to Dinesh from NexGen, and particularly how important it is for the industry and government to work together. Dinesh, over to you.
Thank you. So let me just quickly share my screen. I put a short presentation together that I can cover here. So first of all, thank you for inviting me to be on this panel. I really appreciate it. This is something that I fundamentally believe in, compound semiconductor. Number two, the fact that the government is taking a major initiative in developing the fab ecosystem inside of India. So I'm going to talk to you a little bit about NexGen power systems, and I'm going to give you a real life example of how government and industry collaboration actually yields technology that is completely differentiated in the marketplace, and I'm going to show you some examples of it as well. Now, unfortunately, this is a collaboration that is with the US government, the state of New York, and NexGen power systems. But a similar example can obviously be working with the government as well. So let me jump in here. So one of the key pieces of technology that NexGen has inside its arsenal is a vertical gallium nitride transistor. So you heard a whole bunch of people talk to you about gallium nitride devices so far. Most of the devices that you have heard about are what's called gallium nitride built on a silicon wafer. We are probably the only company on the planet that is actually making gallium nitride on gallium nitride devices. So what's the difference? We actually buy a gallium nitride wafer, and you can see that as the slightly darker blue indication in this cartoon of our device. And on that gallium nitride wafer, we actually grow this drift layer. And then we pattern the device appropriately. Then we grow P-type gallium nitride, and then we make a vertical device. The reason this device is vertical is because current flows from the drain, which is the bottom of the wafer, to the top of the wafer, which turns out to be the source. And this is an E-mode device, which means that the gate, when the voltage on the gate is 0, the device is off. When the voltage goes past threshold, which in this case is 1.4 volts, then the device turns on and the current flows from the drain all the way to the source. This is an EJ FET. E stands for enhancement mode, which means when the device is turned on, it is off. You have to put some voltage on it to actually turn it on. We have over 100 patents on this type of design, the drift layer growth, manufacturing process. And this entire device is actually manufactured in a fab that NexGen has in upstate New York. This is the picture of the fab that we have in upstate New York. It's a 66,000 square foot facility. It's on a 14-acre lot. It's 20,000 square foot of clean room. There's over $30 million worth of tools and machines that we have installed inside that fab. And it's the world's largest GaN dedicated fab, both for R&D and for manufacturing. Now, the way this fab came about is a collaboration between the state of New York and NexGen Power Systems. So the way our deal with the state of New York works is this facility is owned by the state. NexGen Power Systems has a 10-year lease on this facility, and we have the exclusive ability to renew that lease for another 10 more years. The advantage of having this facility is that the amount of money that got spent into building out this facility is roughly $110 odd million. And if a company like ours had to raise $110 million to actually build out this facility, it would have been almost impossible to do. So this is a classic example of the state and a company like ours collaborating together to make this facility into a gallium nitride oriented facility and using such a facility to produce state-of-the-art technology. Now, what do we make in this fab and why is it so different? So I put one slide here that compares our device, which is a power device, and all the other technologies that are available in the marketplace today. So what I'm looking at is silicon carbide IGBTs, super junction MOSFETs, that's the third column, silicon carbide MOSFETs, GaN on silicon HEMTs. Professor Mishra covered this. You heard about silicon carbide MOSFETs. And then this is vertical GaN EJ-FET, which is what we make in our fab. So I'm not going to go through each of these line items, but essentially all the check marks tell you that all the features that are exceedingly important for power engineers to build power systems are fulfilled by what we make in vertical gallium nitride. Essentially, the device that we make is actually a union of the features that silicon carbide MOSFET offers and the features that a silicon GaN on silicon HEMT offers as well. So we'd like to think that vertical gallium nitride utilizes the full benefit of a gallium nitride material and makes a device that's actually purely gallium nitride. It has no silicon, it has no aluminum gallium nitride, none of these more interesting material structures in them. It has N-type gallium nitride, P-type gallium nitride, and metals that actually allow you to make ohmic contact to them. So from here, and this is the uniqueness of NexGen as a company, we're a vertically integrated systems company. So not only do we manufacture the semiconductor that I showed you in upstate New York, we actually make full-blown systems. So from the fab that we make the devices, we actually then make controllers, which we need in order to fully utilize the capabilities of the device that we're manufacturing. These devices are capable of running at 10 plus megahertz switching frequency. And there is no controller in the marketplace that will allow you to run those devices at these switching frequencies. So we make those controllers ourselves. In addition to that, there's a significant amount of work that has to be done on the hardware front, especially when it comes to thermals, magnetics, and other layout parameters that you have to be careful about when you're trying to operate power at very high switching frequencies. So we put that entire infrastructure together and we have created a scalable power platform. That scalable power platform not only allows us to make 20, 30 watt power supplies, it actually allows us to go from 20 all the way to 10 plus kilowatt power supplies, which we're kind of showing you over here. One such example is a 240 watt power supply, which I'm going to show you next. And that will be the first product that we put out into the marketplace. So this is our 240 watt product. That 240 watt product has 4 of the gallium nitride devices that I showed you in it. This is sort of the breakout of what that product looks like. And I have one of them over here that I will actually show on the screen. So this is our 240 watt product. And I'm comparing it with a HP 240 watt, 230 watt product that they offer in the marketplace today. And you can see the size comparison of how small we are compared to the HP product that's out there. Now, the best part is that this entire product design actually happens in India. So we have a systems R&D facility in Bangalore that actually makes and puts this entire subsystem together. So we make our transistors in our Syracuse fab in upstate New York. We ship those transistors to our facility in Bangalore. The Bangalore team puts this entire system together, hardware, software, magnetics, everything that thermal design, everything that goes into it. And we have a contract manufacturer in India as well that actually contract manufactures this entire system for us, and then we ship it worldwide from there. One of the points that was brought about was efficiency savings, and I want to reiterate that over here. So the power supply that I showed you, which is one from, let's say, HP, Lenovo, or Dell, they're typically 88 points of efficiency. Our 240 watt with the vertical gallium nitride device is 94% efficient. And if you have a 6% improvement in efficiency and you make these simple-minded assumptions, you're looking at saving 391,000 metric tons of carbon dioxide from going out into the atmosphere. And as we pointed out earlier, if you have a 2% efficiency gain on pretty much every piece of electronic equipment that's there on the planet, you can actually save, you don't need to deploy roughly 97 coal plants in the marketplace. So not only do we make power supplies out of this, we actually make power supplies that go into data centers. And we have made it so that our power supplies are extremely scalable. So you get the efficiency benefit as well as making sure that the right set of devices get used in the systems that you put into the data center. The same thing works for automotive. There are 3 systems in the automotive: the onboard charger, the DC-DC converter, and the AC-DC inverter. These are the system savings that we actually bring on each one of these subsystems, especially with the 1,200 volt device that we manufacture and put into production, again, into the same fab that I showed you before. We also work in the LED lighting space. This was another one of the applications that we talked about before. So we make the little LED driver that actually goes behind the LEDs, which put out the light, but you need a power system or a power supply that actually drives them. Every system that I've shown you here runs at 1+ megahertz switching frequency. And our devices, like I said, can actually do 10. So 1 is the starting point, and we're basically scaling it up. This is the company. I wanted to point this out because we are located worldwide. The key point here is that our R&D facility is in Bangalore. But one of the key points I wanted to talk about when it comes to building fabs and why the government program is actually so important is because building a fab and working on semiconductor technology is not like working on software, where the capital investment and the capital requirement is significantly lower. So you can have a team of 50,000 people, each of them having 1 computer each, and deploying a small number of servers to actually make sure that the entire team can work together. Setting up a fab is hundreds of millions of dollars of investment. This investment cannot be done over a short period of time. So the outlook for semiconductor and developing semiconductor technologies and fabs is a 10 to 15-year outlook. Such an outlook can only be supported by the government to start off with. So it's very good and it's very welcoming to see that the government is taking an initiative in reducing the cost of this initial capital that will be required to deploy fabs inside of India. But in addition to making sure that we have a fab and we have capital for that fab being subsidized, we also have to make sure that we attract the right talent and nurture the right talent in order to make sure that these fabs can actually run. You need process engineers, you need chemical engineers, you need people that understand device physics to all be coming together to develop a particular technology inside a fab. In addition to that, you actually need significant infrastructure build out. What that means is the gases, the chemicals, all these have been discussed in the last few sessions, and Seema pointed this out as well, which is if you don't have the basic infrastructure that is needed in order to run a fab, you're not going to be able to make the progress that you need. So building a fab is a major undertaking. It needs the support of the government, so it is very great that the government is actually taking that step forward. But it's going to take a fair bit of time in building out a fab, establishing it, making sure that you just don't have one fab, but multiple fabs. Around the fab, you need to make sure that the right talent is built out, the right talent is nurtured. You have the right university and industry relationships in order to make sure that there's a constant flow of people being able to work in the fab and produce the kind of technology that is needed. Doing this for compound semiconductor is even more complicated than doing it for silicon, because compound semiconductors are new, and making sure that you understand how the compound semiconductor industry works, the process works, will also require additional training and resources and skill sets, which have to be developed inside of India in order to make sure that you can have a successful compound semiconductor initiative and a compound semiconductor fab. With that, I'll turn it back to you, Vivek.
Thank you, Dinesh. So as the lunch bell has been rung twice, and there is a reminder. So thank you to all of you. I will quickly summarize the session, and in case there is any time to ask the question. So first, the need of energy efficiency is very clearly established. There is no way, and I will just mention one more thing, that there is a target of 45 reduction in CO2 emissions from 2010 to 2030. So therefore, there is no way that we can escape. And great news is that these wide band gap material and transistors are available and solutions are there. Another key element has been mentioned is really on the ecosystem, that we need to look at it in totality, not in isolation, including the supply chain, otherwise it would not work. Third point, which is again highlighted very well, that manpower-wise, there is quite a lot of, let's say, strength in India, but we need to continue and also develop the electronic systems so that the whole ecosystem becomes richer. So I am sure I have not done the right justice for all that, but quickly, in sake of timing. So,
sir, with
please.
your permission, I think we'll have the questions offline. And sorry for that, because of we are behind schedule. The motivational injection prior to lunch will be done after lunch. So we'll break for lunch, and the motivational aspect you can take offline. Outside the questions, panelists will be available. You can take it offline.
Thank you to all panelists.
Yes, we would like to thank who have joined on the virtual mode, and thank you very much. And I'm pretty sure you will understand why we are taking the questions offline. Thank you very much. Have a great lunch, and do come back at 2 p.m. Namaskara.
We're all set, right?